This is DeepMind, the podcast, and I'm Hannah Fry. Over the last year, I have been getting an inside look at current research into artificial intelligence, or AI. And we've been talking to scientists, researchers and engineers about how things stand and where we're heading, tracing the fast-moving story of one of the biggest challenges in science today. So if you want to be inspired on your own AI journey, then you've come to the right place. Up until now in this series, we have largely looked at what AI is capable of in the lab or in the world of games. But the ambition of people working in AI is to help solve problems in the real world. Right now, people are trying to use AI to help with everything from predicting traffic jams to monitoring endangered species. And here at DeepMind, they've also been working on a few things. Now, we could call them case studies, but where would the fun be in that? So I'll tell you what, let's have one of those big trailer things, shall we? In this episode, we learn how AI might potentially help save the sight of thousands of eye disease sufferers.
We get the output from the first neural network, and we can interrogate that as doctors, making decisions for our patients.
Help break down the enigma of protein folding.
We can learn what the process is, or a description of the process, so that we can take a sequence and then predict its structure.
An impact on our growing energy demands.
If that waste heat isn't taken care of somehow, it will literally melt your laptop.
First, I want you to meet Sims Witherspoon. Sims is originally from South Carolina. She's now the program manager at DeepMind, and she is a big believer in the potential benefits that AI can bring.
When people think about DeepMind, if they think about games, they're largely thinking about the research side. But trying to solve for intelligence is literally to use that intelligence to make the world a better place. The world has no shortage of problems we need to solve. We've got some really big ones, some smaller ones, but for the areas of immense complexity, things where there's lots of data and lots of permutations or a huge combinatorial space of possibilities, sometimes that's really daunting for human brains to try to figure out.
Stuff in the real world is just really complicated.
Yeah, it's really complicated, and real world data is really messy, but if we can use AI to try to find a path through that complexity, then we can solve our problems faster than we could if we were trying to do it on our own.
Nowhere is that more true than in medicine. In 2016, DeepMind partnered up with Moorfields Eye Hospital NHS Foundation Trust in London to try and apply deep learning to eye scans. With the number of people suffering from sight loss in the UK set to double by 2050, the trial had the potential to be hugely impactful. Piers Keane is a consultant ophthalmologist at Moorfields Eye Hospital and National Institute for Health Research, and knows firsthand about the demands placed on doctors.
One of the huge problems that we have in ophthalmology, not just in the UK, but all around the world, is the huge number of patients that we have to deal with. So in particular, in the National Health Service, we get nearly 10 million clinic appointments in the UK every year. And that's actually 10% of all clinic appointments across the whole NHS. And it's a number that's increased by more than a third in the past 5 years.
Why has it increased?
So I think it's increased because of the aging population. I think it's increased because certain diseases like diabetes are on the rise. And so we just have to deal with a lot of eye problems related to that. So for example, I can tell you about just one condition, which is age-related macular degeneration, or AMD. And AMD is the commonest cause of blindness in the UK, commonest cause of blindness in Europe and in North America as well. And for just that one condition, nearly 200 people develop the blinding forms of AMD every single day just in the UK. And so the challenge that we have is that those people have to be seen and treated in an urgent fashion. The problem then is that, for example, in 2016, Moorfields Eye Hospital in London, where I work, received 7,000 urgent referrals from the community as possible wet AMD, the blinding form of this condition. But of those 7,000 referrals, only 800 patients actually had the severe form of the disease.
With so many people getting urgent referrals, it's inevitable that patients are going to have to wait weeks to be seen by a specialist. And during that time, you have thousands of people who think they've got an eye disease that will threaten their sight, who don't actually need to worry. And hundreds of people with a curable condition whose sight could be saved, but is slipping away while they wait. Piers told me about one of his patients, Elaine Manor.
Elaine lost her sight from macular degeneration in her left eye completely more than 10 years ago, before there was good treatment. And in 2013, she started to develop blurring of vision in her good eye. She went to her high street optometrist, who looked into her eye and said, "I think you're developing AMD in your good eye. You need to be seen and treated urgently, because now we have good treatments for this." She got an appointment to another hospital in the NHS, and it was 6 weeks later. So can you imagine if you were at home and you're losing your sight in your good eye, and you're told you have to wait 6 weeks when there is a treatment that's available? And if that was my family member, I would want them treated in 6 days, not in 6 weeks.
Here is where the AI comes in, and the idea is simple. Patients who are referred to Moorfields will already have had pictures taken of the back of their eye by their doctor or the optometrist in their high street opticians. These are 2- and 3-dimensional images known as OCT scans that can show up any one of 50 different diseases. If you can use artificial intelligence to filter through those images first and triage the patients, you can flag the people with a serious disease, get them in front of a doctor sooner, give them an earlier diagnosis, earlier treatment, and potentially save their sight.
Before artificial intelligence and before the recent successes of deep learning, the traditional approach to programming an algorithm to recognize a photo of a cat, for example, would be you would write all the code to describe the features of a cat. Cat has whiskers, cat has a tail. Then you'd say some cats don't have a tail, some cats don't have fur, etc., etc. And you would try and write thousands or hundreds of thousands of lines of code to describe that. With deep learning, we don't do that. With deep learning, we show many examples, often thousands or hundreds of thousands of pictures of cats to a neural network, and it will extract the features of interest itself and learn how to recognize a cat. Well, we simply do the same thing, but with eye diseases.
The machine doesn't care whether it's looking at cats or the backs of eyes. It's the same.
Yeah, to a large extent, yes. And I think the reason why this collaboration has been successful so far is because Moorfields Eye Hospital is one of the oldest, one of the largest eye hospitals in the world. And we have huge numbers of OCT scans to train these neural networks.
Does it work then?
I think the results are amazing. I think they're jaw-dropping. I think that the algorithm we've created is on a par with world-leading experts at Moorfields in triaging these OCT scans.
But there is quite a big difference between spotting cats in pictures and picking out eye disease. For something so important, how do you know the algorithm is getting it right? How can a consultant be sure to see what the algorithm saw, or feel confident to overrule it if they don't agree? Well, the key, Piers told me, is about building an AI that doesn't just tell you what it's found, but also shows you. And to do that, the AI needs not one neural network, but 2.
So the first neural network is trained to identify all the disease features on the scan. And the second neural network is trained to take those disease features and to use them to make a diagnosis on the scan.
So it's first going through and kind of highlighting areas that don't look totally normal.
Yeah.
Anything that looks suspicious.
Yeah.
And the second one's coming in, explaining what's going on all of those, and using that to come to a final decision.
Exactly, yeah.
And you can see all those areas that first neural network has highlighted.
Yes, so that's one of the great advantages of this approach. We get the output from the first neural network, and we can interrogate that as doctors making decisions for our patients. So if you've got bleeding in the retina, or if you've got leakage of fluid and waterlogging of the retina, it will highlight all of those features. So if you see that a patient has diabetic eye disease, then you can see the very typical features that have led it to make that decision, which gives a lot of, I think, reassurance for healthcare professionals who would be using this.
There's a double whammy with this approach. Not only can it reassure the consultants, helping them with the diagnoses they're already doing, but there is hope that the AI might one day also be able to advance our understanding of the eye itself. In 2018, another group of researchers decided to see if they could use deep learning on images of the retina to predict the sex of the patient. Now, the best an eye doctor could manage would be a 50-50 guess. But to their astonishment, the algorithm got 97% right. No ophthalmologist in the world has any idea what it is that this algorithm is picking up on in the photograph, or any theory as to why the male and female eye might be structurally different. But the AI has found something that they're now trying to understand. And in the Moorfields study, even when the algorithm gets the diagnosis wrong, it might still be picking up on something that the professionals hadn't spotted.
What was interesting was that when we looked at the cases that the algorithm got wrong, we actually had to take a step back, because it seemed like some of those cases were very ambiguous, challenging cases where maybe the algorithm had made the right answer and our gold standard was at least open to debate.
Really?
So really kind of like jaw-dropping the results that we were getting.
Jaw-dropping indeed. So that's AI dipping its toe into the world of medicine. But how about one of the most fundamental problems in science?
When I spoke to a very senior researcher about what he thought were the most significant problems in biology, his top problem was understanding the brain and how that works. His second problem that he thought was the most important was understanding how proteins fold.
This is Sandy Nelson, a product manager for DeepMind's science program. And as Sandy told me, it's hard to overstate the importance of proteins. It is the most cited topic in 50 million scientific papers.
So many of the terms we're used to when we're thinking about medical conditions are actually underlying proteins. So we think about the immune system and how that works. Well, that's proteins. We think about hormones. We know that regulates so many functions in our body. So, of course, drugs are a lot to do about small molecules interacting with proteins, but there's many other ways in which proteins are important for thinking about, say, disease. So we know, for example, Alzheimer's and some of those neurodegenerative diseases are to do with proteins, or proteins are implied.
Proteins are the building blocks of all living systems. Stretched out straight, they're just big, long chains of amino acids, a bit like a ribbon. But they fold in on themselves and make these giant three-dimensional structures stuck together with peptide bonds. Now, the number of different ways a protein could fold is vast. Think origami here, except mind-bogglingly complicated human microbiological origami with 10 to the power of 300 possibilities. And scientists care a great deal about exactly what shape those final folded proteins end up as.
Part of the reason proteins are so useful for taking part in so many biochemical processes is because they're specific. They can target very, very specific points in some process. That specificity comes from the uniqueness of their shape. So when we think about proteins are the go-to molecule for anything you need to do in a living animal, if you want to try and understand why some of the proteins have gone wrong or to create some kind of intervention, understanding that process of creating structure from sequence is a first step on maybe designing proteins or understanding why it might go wrong.
The function of the protein, whether it's to detect light in the eye or fight disease or speed up reaction rates, is determined by its unique three-dimensional structure. The question is, how does the protein go from one state to the other, from the ribbon to the final folded structure?
What is the objective here then? Is it that, in the end, you want to create something where I tell you a sequence of amino acids and you tell me what the structure will look like?
So at its simplest level, yes. If you could do it as accurately as it can be done in a lab, that saves a huge amount of effort.
In theory, you can just observe the shape of the final folded structure. The most common way of doing this is by bombarding crystals of the protein with X-rays and inferring its shape from the way that these beams are scattered. But that is hard to do. It can cost hundreds of thousands of dollars for each protein structure and take months or even years of work. It's so hard, in fact, that Max Perutz won a Nobel Prize in 1962 just for figuring it out for one single protein, hemoglobin. There is an alternative, though. The final structure of the protein is actually determined by the chain of component parts, the forces and charges that are acting on each of those individual amino acids. So in theory, you could use the physics to predict how the protein ribbon is going to fold, but it's going to take a lot of number crunching.
So if you had a gigantic enough computer, supercomputer level, I could give you a string of amino acids and you could tell me what shape it would end up as. But the problem is that we just don't have the computing power to crunch through it.
Not at the level of modelling all the forces, so we can explain why the protein folds the way it does using our understanding of chemistry and physics. But because of the size and the complexity of the molecules, there are so many forces, we can't model everything.
And here's where AI comes into it.
We think that there's another level of abstraction where we think we can maybe find a summary description of all those forces. And that's again too hard to come at through analysis, but maybe we can learn that because we've got a huge data set which says, well, this sequence folds this way, and we know that that's reliably the case. So using machine learning, maybe we can learn what the process is or a description of the process so that we can take a sequence and then predict its structure.
Here is a problem with a very clear objective. Correctly predict how a chain of amino acids is going to fold, and a vast, vast number of possible ways to get there. AI is perfectly placed to cut through that complexity. The only problem is that even with AI on your side, these things are so enormously complicated that you still can't cut a clear path to predicting how a protein might fold based only on the physics. Thankfully, though, there is a trick that you can use to simplify the problem and give your AI a head start. The fact that proteins are so diverse can help you constrain the problem. Although I should warn you, as a mathematician, I found this stuff pretty hard to get my head around. So I'm going to try and walk you through it nice and slowly. Proteins, like organisms, have a long evolutionary history. There can sometimes be small random mutations in the string of amino acids. Every now and then, a mutant protein will differ from its normal version on just one of its corners, where if you unravelled it back into the ribbon of amino acids, the markers of that mutation would show up in more than one spot. You can imagine this as though you've got your folded ribbon scrunched up in some complicated shape in your hand, and then you take a felt tip pen to one corner of it. Now, if you unfolded your ribbon and flattened it out, you would see that the pen would have stained various spots along its length. So working backwards then, if you start with a flattened ribbon and notice something strange in a few different places, marks that hint at a consistent mutation, you know that however the protein ends up being folded, you found a big clue. Those stains must have to be next to each other in the final protein. Collect up all of those clues and you have greatly simplified your problem.
Is it like you've got this vast sort of landscape of options and you're trying to build walls to pen yourself in?
Yes, that's exactly right. Because these proteins are so large, they could fold in so many different shapes. So we need to find clues that allow us to eliminate a whole mass of shapes so we can concentrate just on a much smaller number.
You're making the problem smaller.
That's right.
You're listening to a podcast from the people at DeepMind. Now, every 2 years, there is a big protein folding competition called CASP, Critical Assessment of Structure Prediction Competition. Over the course of 3 months, academics from around the world compete to predict the structures of amino acids using algorithms. The structures of these particular amino acids have already been confirmed through traditional observation, so it's possible to judge who comes closest. And in 2018, DeepMind entered its AI program, AlphaFold.
We had a look at how other people did protein folding, and we saw how they used evolutionary information. And what other people had been doing was they'd been looking at a sort of binary constraint which said these two amino acids should be in contact or shouldn't be in contact. Whereas what DeepMind did is we looked at the probability of different distances between those amino acids. So that's really like just saying, well, we tried to retain some more information or learn a better function for describing that relationship between proximity of amino acids.
So in terms of the fences that you were building on your landscape, I mean, I'm going quite far with this analogy now.
That's fine. That's a very good plan.
You were making sure that you weren't throwing away any information.
That's right. Our fences were more subtly defined or a bit more clearly delineated, or they were less fence-like and more like just a sort of...
Hillocks.
Hillock, that's right.
Nice. But that actually ended up making the prediction more accurate.
Yes, that's right. So it's a very, very complicated function, but we were able to learn that. And so once we're able to learn to kind of essentially retain that extra information, that's one of the key things that made our system more successful.
With the problem reduced, the AI could get to work, doing what it does best. For 3 nail-biting months, the DeepMind AlphaFold team worked on the competition, turning sequences of amino acids into predictions of 3-dimensional folded shapes.
We didn't have any strong signal which told us how well we were performing. We could see that we were not perfect in many cases, so it was very hard to find out how well we were doing compared to other people. There's so many fantastic researchers that were publishing great results. Until we actually went through that sort of organized assessment, very, very hard to really figure out how well we were doing.
And then finally, it was the moment of truth. Of the 43 strings of amino acids they were given, the team came closest to correctly predicting the structure for 25 of them. The team that came in second only managed 3, a staggering result by anyone's standards.
You're kind of downplaying this because I was talking to a few academics when this result came out, and of all of the results that have come out of DeepMind, this is the one that's got the scientific community most excited.
Yes, and that's because this is a classical scientific domain. It's a grand challenge in science that many people have worked on. So it's something that many, many scientists care about deeply. They can see what the potential impact is, and it's been known to be a very hard problem. So we've been able to make a step change on a hard problem that's been worked on for over 50 years.
In terms of interventions then, is this just something that biologists and scientists will get very excited about in terms of kind of blue sky research, understanding proteins? Or is it something that could end up having an impact in real people's lives?
So I guess it's similar to all sort of biomedical research. It's fundamental, so it has huge leverage. It essentially will affect many, many things, but it needs to be translated into something specific for it to have immediate impact on people's lives. So, for example, if we think about the drug discovery process, part of that process goes on in labs and is very abstract and all to do with chemistry. But ultimately, that process does produce medicines that we can buy or prescribe, which ultimately will affect our lives. So this is at the start, the early part of that process, for example.
Although the long-term implications of protein folding have the potential to impact all of us, it's not exactly a topic that most of us are coming face to face with on a daily basis. But one issue that we are all facing is that of climate change. You remember Sims, who you met earlier? Well, her team decided to focus their efforts on one specific climate challenge: energy consumption in data storage. And they started by looking for a place we're burning far more energy than we need to, because it turns out your emails are one of the things that are warming the planet.
If you think about the things that we all do online every day, whether that's sending an email, doing a Google search, looking at dog videos on YouTube, the number one videos is cat videos, but for me it's dog videos.
And me.
Nice. All of that requires compute power. And, the information that we, data we send, data that we store, when information's disseminated, all of that runs through a physical space, i.e. data center. Right? And it takes a lot of energy to do all of those actions that we rely on the internet.
Because there are actual sort of physical warehouses that are holding all of those cat videos.
Yes, they are physical spaces. And if you think about the amount of energy they consume, a data center, in a large industrial kind of setting can consume the same amount of energy as a small town. These things are massive and they require a lot of energy to run. They also require a lot of energy to cool.
All those emails sitting in your inbox, the 4 dog videos you're streaming simultaneously, the request you sent to the server to download this very podcast, every one of those things requires computing power in a data center somewhere. Collectively, data centers now use 3% of the world's energy, the equivalent of a whole new country that just popped up on the map a few years ago. And all that computing generates heat. Lots and lots of heat.
If you imagine how hot your laptop gets when you're streaming Netflix or the 4 videos online, imagine that but multiply it times 1,000,000. If that waste heat isn't taken care of somehow, it will literally melt your laptop, or in the case of a data center, it will melt your server. That's why your laptop has a fan. That's why data centers have cooling that needs to happen there. We have to keep them at a temperature so they don't melt, and you and I can get our dog videos off YouTube.
And I guess just cooling down those data centers takes up a vast amount of energy.
Yes, it does. We're talking about chillers required that are the size of buses in order to keep them cool.
And this is where AI comes in.
So imagine you were trying to control the cooling of a data center, and a human being who, is usually a facility manager, data center operator, just has 2 kind of dials to control. And that was all you had to do to control the entire center. Now, that is a vast oversimplification.
Like
right?
a fan and aircon.
Yeah, exactly. Wow. Just those 2. You could figure out the best, is it just aircon? Is it just fan? Is it both? Is it neither? That's not that many options, right? You could figure that out. But when it turns into a huge number of pieces of equipment with set points on every single one, which are all things you can change by some degree that then interact, all of a sudden you've got a vast number, literally a number of options that is in the billions. And that's just too much for a facility manager, a data center operator, a human being to try to control. So this is where we think it's the perfect space for AI, because AI can ingest a vast amount of information, more than the human brain can, and can help us figure out which of those permutations, which of those combinations actually is the optimal path forward.
How does AI cut through all of this complexity, though?
We can ask a model to figure out, okay, we want to keep the data center at a certain temperature, but we want to use less energy to do that. Here are all of the ways that you can manipulate this system. Please figure it out.
The setting might look quite different to a game of chess or Go, but the principal ideas here are exactly the same. Again, you have a very clear objective, namely keep the center cool while using as little energy as possible, and a vast number of possibilities of how to get there that the AI has to find a path through. And once it does,
the AI tells you how all of the dials should be set across the center.
Exactly. What set points to change and by how much to change them.
And does it work?
It does work. That's the best part about it. We saw that with direct AI control, i.e., getting those recommendations and having AI feed them directly back into the physical infrastructure of the data center, going through lots of safety constraints, we saw a 30% reduction in the amount of energy required to cool Google data centers.
Which is massive.
Which is massive, and a really exciting number.
Now, I have to confess, I've seen the graph of what happened when you put the AI in direct control of all of the dials. And it is staggering. I mean, you've got this sort of bumpy line that goes along about how much energy is being used. And then it looks like those graphs where the pound crashes after some terrible news. It just drops off a cliff. And then you kind of have it bumping along the bottom of the graph, at which point you take the AI away from being in control and switch back over to human control. And it just jumps straight back up to where it was before. It's amazing. Is the AI running the cooling system in the data centers right now?
Yes, it is, which is fantastic, and hoping to roll them out to even more in the future now that we've kind of proved that this works and works well. With more data, with more practice, in other words, the AI gets better over time. So 30% is a fantastic number, but it's increasing. Rules and heuristics don't get better over time, but AI does. That's the best part about these systems.
And that is why there is so much excitement about AI's potential here at DeepMind and at AI labs around the world. If you would like to find out more about applying AI to energy, healthcare and scientific problems, or explore the world of AI research beyond DeepMind, you'll find plenty of useful links in the show notes for each episode. And if there are stories or resources that you think other listeners would find helpful, then let us know. You can message us on Twitter or email the team at podcast@deepmind.com. You can also use that address to send us your questions or feedback on the series. Now, shall we have another break?